Right now, somewhere in tonight's sky, the nearest black hole to Earth is quietly moving through the Milky Way. And the unsettling part is that we don't actually know where it is. The closest black hole we've managed to discover lies about 1,560 light-years away, hidden beside an ordinary sun-like star in the constellation Ophiuchus. When astronomers finally weighed the invisible object in 2022, it turned out to be nearly 10 times the mass of our Sunday. But that distance is almost certainly not the real answer. It is only the distance to the nearest black hole we've been fortunate enough to find. Across the Milky Way, there may be 100 million black holes giving off no light at all, and almost all of them remain completely invisible to us. One of them is very likely much closer than 1,500 light-years, quietly hiding among the ordinary stars you would never think to question. Before we begin, if you're kind enough, a gentle like or a quiet tap on subscribe would mean the world to me. It's a small gesture, but I hold it with deep gratitude, because every bit of your support keeps this tiny universe alive and reminds me that these quiet stories are kept alive by hearts as kind and thoughtful as yours. Now, let's begin with a single trembling star. Follow it into a hidden population of 100 million invisible worlds, and discover why the most honest answer to the question, how far away is the nearest black hole, may be one that science still cannot give. Picture the summer sky over Ophiuchus, the ancient constellation imagined as a man holding a serpent, hanging low above the southern horizon. Among its ordinary-looking stars is one that attracted little attention for decades. It has nearly the same mass as the Sun, nearly the same surface temperature, and much the same warm, yellow light. If it replaced our own Sun, the daytime sky on Earth would hardly seem different. Yet this unremarkable star is doing something that should not happen on its own. It follows a slow, elliptical path around a point in space where every telescope sees only darkness. Stars do not orbit empty space. Every stable orbit tells us that gravity is acting on two objects, even when only one of them can be seen. The visible star is not circling nothing. It is moving around a shared center of mass with an unseen companion. You can picture the same effect if you have ever swung a heavy bag while standing on smooth ice. The bag circles around you, but you shift slightly as well. Someone watching from a distance could estimate the bag's mass simply by measuring your motion. That is exactly the method astronomers use. The motion of the visible object reveals the mass of the invisible one. When the European spacecraft Gaia measured this sun-like star completing an orbit every 186 days, its tiny motion provided exactly that clue. From the size of the orbit, astronomers calculated the mass of the unseen companion. The answer was about 10 times the mass of the Sunday. That single number shapes everything that follows. 10 solar masses packed into an object that emits no detectable light. Not visible light. Not infrared radiation. Nothing. Faced with a result like that, astronomers do not begin by celebrating. They begin by looking for mistakes. Could the unseen companion simply be an unusually faint star? The physics rules that out quickly. A normal star with 10 times the Sun's mass would be thousands of times brighter than the Sun itself. It would dominate the system so completely that the smaller star would be almost impossible to notice. Instead, the spectrum shows only the quiet sun-like star and nothing else. What about two smaller stellar remnants sharing the mass? That possibility also fails. A pair compact enough to fit the observations would not remain stable over astronomical timescales. As each ordinary explanation was tested, it proved less consistent with the data than the one before. Eventually, only one explanation continued to match every observation. The unseen companion was almost certainly a black hole. The person leading that analysis was Karim El-Badri, a young astronomer who had become well known for questioning black hole discoveries rather than announcing them. Earlier in his career, he had re-examined several high-profile candidates and shown that some could be explained without invoking a black hole at all. That reputation shaped the way he approached this system. Instead of trying to confirm the result, he tried to eliminate it. He tested every alternative explanation that had overturned previous claims, collected follow-up observations from multiple observatories, and repeatedly asked whether the data could still be explained by something ordinary. Each possibility eventually failed to account for the observations. By the time the study was published, the conclusion was not built on a single dramatic measurement. It rested on the gradual elimination of every simpler explanation the team could find. The discovery was published in 2022, and Gaia BH1 became the closest confirmed black hole ever identified. Its distance is about 1,560 light-years. Numbers that large are difficult to picture, so it helps to compare them with distances we know. Light travels from the Moon to Earth in about 1.25 seconds. It reaches us from the Sun in just over 8 minutes. The light arriving from Gaia BH1 tonight began its journey when the Roman Empire was still collecting taxes. It crossed 15 centuries of space while civilizations rose and fell on Earth before finally reaching our telescopes. On a human scale, that is almost impossible to grasp. On the scale of the Milky Way, which spans roughly 100,000 light-years, it is comparatively nearby. If our galaxy were compressed to the size of the continental United States, Gaia BH1 would be only about 50 miles away, close enough to reach in a morning drive. That is where the discovery becomes especially interesting. Gaia BH1 was not detected because it emits light of its own. It was detected because it happens to orbit alongside a bright sun-like star. Without that companion, the system would look completely different to us. There would be no stellar motion to measure, no orbital wobble to analyze, and no direct sign that a 10 solar mass black hole was passing through that region of the galaxy. The object itself would still be there. Our best telescopes simply would not know it. That idea stayed with me long after I finished reading the discovery paper. Not because of the black hole itself, but because of the ordinary star beside it. It is remarkably similar to our own sun and has likely orbited its unseen companion for billions of years. If that system also contains planets, as many sun-like stars do, those worlds would have spent their entire histories with a black hole as a permanent neighbor. Their orbits could remain stable. Their skies might look entirely ordinary. Whatever weather or seasons they experience would unfold much as they always have. We often associate black holes with violent events. Gaia BH1 reminds us that, once formed, many of them simply become quiet members of ordinary planetary systems. So, for now, the record remains 1,560 light-years. But it is worth remembering what that record actually represents. It is not the distance to the nearest black hole. It is the distance to the nearest black hole we have been able to identify. Current estimates suggest that the Milky Way contains roughly 100 million stellar black holes. Yet only a few dozen have been confirmed through observations. A few dozen out of 100 million. It is like trying to estimate the population of an entire country after meeting only a handful of people. The rest are not missing. They simply have not revealed themselves yet. That leaves us with two conclusions that are both difficult to escape. We know exactly where the nearest confirmed black hole is. At the same time, everything we understand about black holes suggests it is almost certainly not the nearest one that exists. If isolated black holes produce no light, have no companion star, and leave no observable signature, how many of them could already be drifting through our corner of the Milky Way without giving us any way to notice they are there? Imagine walking into a vast warehouse with the lights turned off, carrying only a small flashlight. As you sweep the beam across the room, it catches a few scattered objects, a crate here, a pillar there, something half hidden in the distance. By the end of the night, you could make a careful inventory of everything your flashlight revealed. The list would be accurate, but it would never describe everything inside the warehouse. It would describe only the small fraction your light happened to reach. For much of the history of black hole astronomy, that was essentially our situation. The flashlight in this case was X-ray astronomy. To understand why, it helps to look at how most black holes were discovered before Gaia BH1. A black hole by itself emits essentially no light. But if it orbits close to a living star, the situation changes completely. Gravity can pull gas away from the star, drawing it toward the black hole. That gas does not fall straight inward. Because it already carries angular momentum, it spreads into a rapidly rotating accretion disk. As the material spirals closer to the black hole, collisions and friction heat it to millions of degrees, turning the disk into an intense source of X-rays before the gas finally disappears beyond the event horizon. The black hole itself remains dark. What astronomers detect is the radiation from the hot gas surrounding it. That method gave us the first confirmed black holes, and it was remarkably successful. At the same time, it came with an unavoidable limitation. It could only reveal black holes that happened to be actively feeding. The system needed a nearby companion star, and the transfer of gas had to be energetic enough to produce detectable X-rays. Remove the companion star, or stop the flow of gas, and the signal disappears. An isolated black hole produces no accretion disk, no bright X-rays, and almost nothing that gives away its presence. Astronomers refer to these objects as dormant black holes. The name reflects a simple observational fact. They are not inactive. They are simply difficult to detect. Over several decades of X-ray astronomy, only about 20 stellar black holes in the Milky Way were firmly identified through this process. Every one of them was found because it happened to be accreting material from a nearby companion. Even those systems are not continuously bright. Many spend long periods in relatively quiet states before becoming active again. Catching one often depends on observing it during the right phase of its evolution. In other words, our view of the black hole population depended not only on where we looked, but also on when we happened to be looking. It took time to appreciate what that limitation implied. For much of the 20th century, accreting systems made up almost every confirmed stellar black hole we knew. It was natural to build our picture of black holes around the examples we could observe most easily. But those systems were never expected to represent the whole population. Stellar evolution predicts that most black holes should spend their lives in far quieter conditions. Many should have no nearby companion at all. Others may orbit stars without drawing enough material to produce detectable X-rays. The largest part of the black hole population was probably not hiding at the edge of the observable universe. It was hiding among the ordinary stars of our own galaxy, leaving almost no observable trace. Consider what an isolated, dormant black hole actually offers an astronomer. It emits essentially no light of its own, so ordinary telescopes have nothing to detect. It is not accreting material, so it produces no bright X-rays. Even a black hole with 10 times the Sun's mass has an event horizon only about 60 kilometers in diameter, far too small to block any noticeable portion of the sky behind it. It has no solid surface, no atmosphere, and no reflected sunlight to reveal its presence. Most astronomical techniques depend on detecting light that an object emits, reflects, or blocks. An isolated black hole does almost none of those things. Its gravity remains the only practical clue, and even that is useful only under very specific circumstances. That is what made Gaia BH1 such an important discovery. It was not actively feeding, so it never announced itself through X-rays. Instead, Gaia detected the tiny motion of its companion star as both objects orbited their shared center of mass. The discovery came from an entirely different observational method. The first dormant black hole identified this way turned out to be closer than almost every accreting system discovered over the previous half-century. That result was revealing. The black holes had not changed. What changed was our ability to recognize a different part of the population. That immediately raises an important question. If a new observing technique quickly uncovered a closer black hole than decades of X-ray surveys had found, what exactly was the older catalog measuring? The answer is not the distribution of black holes themselves. It is the distribution of black holes that happen to be detectable with that particular method. Every object in the catalog is real. Every distance is carefully measured. Even so, the catalog represents only the fraction of the population that leaves observable signatures. Like every astronomical survey, it reflects the strengths and limitations of the instruments that produced it. Astronomers working in this field have long been aware of that distinction. The known accreting systems and the few dormant black holes identified so far were never expected to represent the entire galactic population. They are simply the objects that reveal themselves most clearly. Most stellar black holes are expected to spend their lives in much quieter conditions. Many probably have no nearby companion star. Others may orbit companions without producing enough accretion to become bright X-ray sources. The black holes we have identified are therefore best understood as a small observational sample rather than a complete census of the Milky Way. That brings us to the number astronomers return to again and again. Roughly 100 million stellar black holes are thought to exist in the Milky Way. The estimate is not based on direct observations of those individual objects. Instead, it comes from what we know about how stars are born, evolve, and die. If only a few dozen have been identified directly, where does a number as large as 100 million come from? And how much confidence should we place in it? The answer comes from a surprisingly old idea. Long before telescopes existed, people learned that it is often possible to estimate the size of a population without counting every individual member. A farmer who knows how many lambs are born each year and how long sheep typically live can make a good estimate of the total flock without gathering every animal into one field. Astronomers use much the same logic. In this case, the births are the deaths of massive stars that leave black holes behind. The flock is the entire Milky Way. To understand where that number comes from, we first have to ask which stars are capable of becoming black holes. Most are not. Our own Sun, for example, will never form one. In about 5 billion years, it will expand into a red giant, shed its outer layers, and end its life as a white dwarf roughly the size of Earth. That is the expected fate for the overwhelming majority of stars. Black holes form only from the most massive stars, typically those born with several tens of times the Sun's mass, though the exact threshold depends on the details of stellar evolution. Such stars are genuinely rare. For every one of them, the galaxy produces hundreds of Sun-like stars and many more low-mass red dwarfs that will survive for trillions of years. That imbalance is not simply an impression. It follows a well-established statistical pattern known as the stellar initial mass function, first quantified by Edwin Salpeter in the 1950s. The relationship is steep. As stellar mass increases, the number of stars born at that mass falls rapidly. The stars capable of producing black holes occupy only the extreme upper end of the distribution. At the same time, those massive stars evolve extraordinarily quickly. A star with 20 or 30 times the Sun's mass typically survives only a few million years before collapsing, compared with roughly 10 billion years for a star like the Sunday. Although such stars are rare at any one moment, the Milky Way has produced generation after generation of them over billions of years. Their remnants accumulate even as the stars themselves disappear. That accumulation is the key to the estimate. Once a stellar black hole forms, it remains part of the galaxy for timescales far longer than the current age of the universe. Hawking evaporation is real in theory, but for stellar mass black holes it takes vastly longer than any timescale relevant to galaxies. From the perspective of galactic evolution, black holes are effectively permanent. That means astronomers are not counting only the massive stars that exist today. They are estimating how many massive stars have lived and died throughout the history of the Milky Way, and how many of those deaths likely produced black holes that still exist. Because star formation has continued for nearly the entire lifetime of the galaxy, the total steadily grows over cosmic time. Today, the Milky Way forms new stars at a rate of roughly 1 to a few solar masses each year. The exact rate has changed over the galaxy's history, but observations and models allow astronomers to reconstruct its overall star formation record. Combining that history with the stellar initial mass function identifies the fraction of stars born massive enough to collapse into black holes. Integrating that process over billions of years produces a total in the tens to hundreds of millions. Most modern estimates place the population at around 100 million stellar black holes. That conclusion does not require observing every individual object. It follows from the same population-based reasoning used throughout astronomy and many other branches of science. One of the striking things about that estimate is how much confidence it carries despite the scarcity of direct detections. The exact number is uncertain, and published studies span a broad range, from several tens of millions to perhaps close to 1 billion stellar black holes, depending on the assumptions built into the models. Even so, the underlying ingredients are among the best understood in astrophysics. Stellar birth rates, stellar evolution, and stellar lifetimes have been studied for decades and are constrained by a wide range of observations. The uncertainty lies in the details, not in the overall conclusion. Whether the true number is 50 million or 500 million, the Milky Way almost certainly contains an enormous population of black holes that have never been observed directly. A population of 100 million is difficult to picture on its own. The Milky Way contains somewhere between 100 billion and 400 billion stars. Compared with that enormous population, the average comes out to roughly 1 stellar black hole for every 1,000 stars. A simple analogy helps. Imagine a stadium filled with 100,000 people, each holding a small candle. Among that crowd would be about 100 people without a light. From the stands, you would never pick them out individually. The surrounding lights would overwhelm them completely. Even so, they would still be part of the crowd, whether you noticed them or not. That ratio has an important implication. Black holes are not expected to occupy some special region of the Milky Way. They formed from ordinary massive stars, so their descendants remain mixed throughout the stellar disk. The Sun sits in a fairly typical part of one of the galaxy's spiral arms. There is no evidence that our neighborhood is unusually rich or unusually poor in stellar black holes. As a first approximation, the local proportion should resemble the galactic average. If one black hole exists for roughly every 1,000 stars across the Milky Way, we should expect a similar proportion among the stars surrounding the Sunday. That is where the question becomes much more concrete. We began with a confirmed black hole about 1,560 light-years away. But if stellar black holes are distributed throughout the galactic disk in roughly the same way as the stars that produce them, their typical spacing should not be a mystery. It is something we can estimate. Given an approximate population and the volume those objects occupy, what distance would we expect between neighboring stellar black holes? And how does that expectation compare with the nearest confirmed example we have actually observed? The calculation is simpler than it first appears. If we know how many objects occupy a given volume, we can estimate their average number density. From that density, we can estimate the typical separation between neighboring objects. The same idea is used in many areas of science, from estimating the spacing between trees in a forest to the average distance between galaxies in the universe. The mathematics is straightforward. The challenge lies in choosing a realistic description of where the black holes actually reside. They are not distributed throughout a giant sphere surrounding the Milky Way. Like the massive stars that created them, stellar black holes are concentrated within the galactic disk. That disk is about 100,000 light-years across and only a few thousand light-years thick. Most of the stars, gas, and stellar remnants are confined to that relatively thin structure. If we distribute roughly 100 million stellar black holes throughout that volume, using the same broad distribution followed by the stellar population, the typical separation between neighboring black holes comes out to on the order of 1 to 200 light-years. The exact value depends on the assumptions built into the model, but the important result is that it is measured in hundreds of light-years rather than thousands. At first, those numbers seem reassuring, but they describe the Milky Way as a whole, and our own part of the galaxy is not perfectly average. The stellar density is much higher toward the galactic center than it is here in the quieter outskirts where the Sun resides. So it makes more sense to look at the stars in our immediate surroundings rather than averaging across the entire galaxy. Surveys of the solar neighborhood show that there are roughly 1,000 stars within about 50 light-years of the Sunday. If the galactic average of about one stellar black hole per 1,000 stars also applies locally, then we arrive at a simple statistical expectation. On average, our local neighborhood should contain roughly one stellar black hole within a region of that size. That statement deserves to be interpreted carefully. It is not a detection. It does not identify a particular object or a particular direction in the sky. It is simply the expectation that follows from applying the average stellar population of the Milky Way to the region around the Sunday. If our neighborhood is reasonably typical and there is little evidence that it is unusual, then the expected number of stellar black holes nearby is of order 1 rather than 0. Whether that expectation happens to correspond to exactly one object, none at all, or several depends on the natural statistical variations found throughout the galaxy. Now, compare that expectation with what we have actually observed. The nearest confirmed stellar black hole lies about 1,560 light-years away. The statistical expectation points to a characteristic distance measured not in thousands of light-years, but in only a few tens of light-years. Those two scales differ by roughly a factor of 30. That difference does not mean the calculation must be exactly right. It means the confirmed discovery almost certainly does not represent the true distance to the nearest stellar black hole. It represents the distance to the nearest one that current observing techniques have been able to identify. There is an obvious objection. A statistical expectation is not a guarantee. Random fluctuations exist, and one region of the galaxy will never look exactly like another. The nearest stellar black hole could easily lie somewhat closer or somewhat farther away than the average estimate suggests. But fluctuations have limits. Reconciling a statistical expectation of only a few tens of light-years with a true nearest distance of more than 1,500 light-years would require our local region to be extraordinarily underpopulated in black holes, compared with the rest of the Milky Way. Current models of stellar evolution and galactic dynamics provide no evidence for such an extreme local deficit. One result comes directly from observations. The other comes from population statistics. It is tempting to trust the observed number more, simply because it has been measured. But the two numbers answer different questions. Gaia BH1 tells us the distance to the nearest confirmed black hole. The statistical estimate describes where the nearest member of the entire unseen population is most likely to be found. Those are not competing conclusions. They are complementary descriptions of the same galaxy, viewed through two different ways of asking the question. We arrive at an unusual conclusion. Statistical arguments suggest that at least one stellar black hole is likely to exist much closer to the Sun than many of the familiar stars that appear in star charts and field guides. If that expectation is correct, the object may have shared our region of the galaxy throughout recorded human history. It would have remained unnoticed, not because it was especially distant, but because it never produced an observable signal strong enough to reveal itself. Before we follow that possibility any further, it is worth remembering how uncertain this search has often been. The history of the nearest known black hole is not a simple sequence of ever closer discoveries. Over the years, several promising candidates were proposed and later revised or rejected as new observations became available. The picture improved gradually as better instruments and better methods reduced the uncertainties. That history explains why astronomers remain cautious whenever a new nearby candidate is announced. Before Gaia BH1, one of the best-known nearby stellar black holes was found in the constellation Monoceros. The system first attracted attention in August 1975, when an X-ray satellite detected a sudden, powerful outburst from that region of the sky. For several weeks, it became one of the brightest X-ray sources ever observed. The event was short-lived. As the outburst faded, the system gradually returned to relative quiet, making it much more difficult to study. Even so, the flare provided the first indication that something extraordinary might be present. The explanation was the same process we discussed earlier. A relatively ordinary star was orbiting an unseen companion close enough for gas to be pulled away from its surface. That material formed an accretion disk around the compact object, where it was heated to millions of degrees before disappearing beyond the event horizon. The system became known both by its X-ray designation and by its variable star name, V616 Monocerotis. Once the outburst ended, however, the X-rays largely disappeared. The remaining challenge was no longer detecting the flare. It was demonstrating what kind of object had produced it. That answer came more than a decade later. In 1986, Geoffrey McClintock and Ronald Remillard carefully measured the motion of the companion star as it completed an orbit every 7 3/4 hours. From that motion, they could calculate the mass of the unseen object. The result exceeded the maximum mass expected for a neutron star, leaving a stellar black hole as the most plausible explanation. The system became one of the first stellar black holes to be dynamically confirmed through measurements of its companion's orbit. In many ways, Gaia BH1 follows the same physical principle. The difference is that Gaia was able to apply it to millions of stars simultaneously instead of studying one system at a time. Looking back, the sequence is revealing. The system first drew attention because of a brief episode of accretion. Only years later did careful orbital measurements establish the nature of the unseen companion. Its distance, roughly 3,000 light-years, made it one of the nearest confirmed stellar black holes known for many years. Had the system never undergone that bright X-ray outburst, it might never have been selected for detailed follow-up observations. Had it lacked a suitable companion star, its mass would have been much harder to determine. The discovery depended on a combination of favorable circumstances rather than on the black hole itself being unusual. Looking back over the history of these discoveries, a clear pattern emerges. The nearest confirmed black hole has never become closer because black holes change their positions. It became closer because astronomers developed new ways of detecting objects that older techniques could not reveal. X-ray surveys first identified systems undergoing active accretion. Follow-up orbital measurements established the masses of many of those compact objects. Decades later, Gaia demonstrated that even non-accreting systems could be uncovered through their gravitational influence on companion stars. Each advance expanded the range of black holes we were capable of finding. The underlying population had not changed. Our observational reach had. That distinction is easy to lose when discoveries are announced. Headlines naturally describe the nearest black hole as though it were a final answer. In practice, every record reflects the capabilities of the instruments available at the time. V616 Monocerotis was the nearest stellar black hole that astronomers could confidently identify using the techniques of its era. Gaia BH1 now holds that position because modern astrometry can detect systems that earlier surveys could not. In this field, nearest confirmed and nearest existing are related ideas, but they are not the same thing. That difference also shapes how future discoveries should be interpreted. When another nearby stellar black hole is eventually announced, the neighborhood will not have changed overnight. What will have changed is our ability to observe it. Each improvement in instrumentation allows astronomers to explore a part of the black hole population that was previously inaccessible. Over time, the nearest confirmed object has generally moved closer as those methods have improved. That long-term trend is consistent with the statistical expectation that many undetected stellar black holes remain much nearer than the closest system we have confirmed today. The history is not perfectly smooth, however. Some candidates that initially appeared convincing were later revised or abandoned as better observations became available. That is not a weakness of the scientific process. It is one of its defining strengths. New measurements are expected to test earlier conclusions, and occasionally those conclusions change. The search for nearby black holes has advanced through both discoveries and corrections. One example became especially well known because of how dramatically the conclusion changed. For a short time, the system appeared to contain the nearest stellar black hole ever reported. It was close enough that one of its stars could be seen with the unaided eye under dark skies. The announcement received worldwide attention in 2020. Over the following 2 years, however, independent teams reanalyzed the observations and reached a very different conclusion. The proposed black hole gradually disappeared from the evidence rather than from the sky itself. Understanding why that happened reveals as much about the scientific method as it does about black holes. In the spring of 2020, astronomers announced that the bright stellar system HR 6819 in the southern constellation Telescopium appeared to contain the closest known stellar black hole. At an estimated distance of about 1,000 light-years, it would have been significantly closer than previous confirmed systems. Because one of its stars is visible to the naked eye under sufficiently dark skies, the announcement quickly attracted attention well beyond the astronomical community. The possibility that a nearby black hole might reside within an otherwise ordinary-looking star system was both scientifically important and easy for the public to imagine. That combination helped make HR 6819 one of the most widely discussed black hole candidates of its time. The original observations appeared to support a straightforward interpretation. One of the visible stars showed a regular 40-day motion that seemed to require a massive, unseen companion. When the orbital solution was calculated, the hidden object appeared massive enough to be a stellar black hole. The proposed model placed a normal star in a close orbit around that unseen companion, while a second bright star orbited farther away. It was a physically reasonable explanation based on the available data, and the announcement quickly attracted worldwide attention. Not everyone reached the same conclusion. Soon after the discovery paper appeared, Julia Bodensteiner and her collaborators re-examined the observations and proposed a very different interpretation. In their model, no black hole was required. Instead, the system consisted of 2 stars that had already passed through an episode of mass transfer. The observations themselves were unchanged. What differed was the physical model used to explain them. Their scenario begins with 2 massive stars born in a close binary system. The initially more massive star evolves first and expands as it exhausts its nuclear fuel. As its outer layers extend toward its companion, gravity allows material to flow from one star to the other. Over time, the donor star loses much of its outer envelope, while the companion gains mass and angular momentum. The result is a binary system in which one star has been stripped down to its hot inner layers and the other has become more massive and rapidly rotating. This process is often described as stellar vampirism, an informal term for mass transfer in close binary stars. Bodensteiner's team argued that HR 6819 represented exactly this evolutionary stage rather than a star orbiting a hidden black hole. Both models explained many of the original observations. One required an unseen black hole. The other replaced it with a hot stripped star whose light was difficult to distinguish from that of its much brighter companion. Distinguishing between those possibilities required additional observations capable of directly testing the geometry of the system. The question was no longer whether both models could fit the existing data. It was whether new observations would favor one over the other. That opportunity arrived in 2022. Astronomers combined observations from the Very Large Telescope Interferometer with high-resolution spectroscopy to measure the relative positions and motions of the stars much more precisely than before. The improved observations directly tested the competing orbital configurations. Instead of relying only on subtle shifts in spectral lines, the geometry of the system itself became measurable. The new measurements strongly favored the stripped star model. They showed two stars orbiting one another every 40 days, consistent with the evolutionary scenario proposed by Bodensteiner and her collaborators. No additional compact object was required to explain the observations. HR 6819 turned out to be an unusually valuable example of binary stellar evolution rather than the nearest known black hole. The original interpretation was replaced not because the earlier team had been careless, but because better observations provided a more complete picture of the system. It was a textbook example of how scientific conclusions evolve when new evidence becomes available. What happened next is one of my favorite parts of the story. The team that had originally proposed the black hole did not defend the claim simply because it was theirs. Instead, they worked alongside the astronomers who had challenged it. The paper that removed the black hole from HR 6819 was co-authored by many of the same researchers who had first announced its discovery, the original discoverers and their critics arriving at the same conclusion together. It was not the kind of ending that attracts dramatic headlines. It was quieter than that, and in many ways more impressive. HR 6819 ultimately became valuable not because it revealed the nearest black hole, but because it showed how astronomy corrects itself when better evidence arrives. Discoveries matter, but the willingness to abandon them when the evidence changes matters even more. And it leaves us with a lesson that cuts both ways as we continue searching for the true nearest black hole. On one hand, it is a warning. A dormant black hole and a stripped, exhausted star can leave behind remarkably similar fingerprints, and separating one from the other can take years of observation and instruments available to only a handful of observatories. Some of the objects we are most eager to find can look almost indistinguishable from systems that contain no black hole at all. On the other hand, the story offers an unexpected kind of reassurance. The same scrutiny that erased HR 6819 is exactly what gives the surviving discoveries their strength. By the time a black hole has survived every serious attempt to explain it away, there is usually very little room left to doubt that it is real. Which brings us, at last, to the instrument that emerged from exactly that process and revealed a black hole no competing explanation could account for. The spacecraft that confirmed Gaia BH1 was never designed to search for black holes, and it never deliberately pointed at one. Its mission sounded almost ordinary by comparison: to measure where the stars are. How does a mission built simply to chart stellar positions end up weighing an invisible object more than 1,000 light-years away? And what made its measurements precise enough to detect a motion so slight that every earlier survey had overlooked it? Hold your thumb out at arm's length and look at it with one eye, then the other. It seems to jump sideways against the far wall. Your thumb has not moved at all. The only thing that changed was the position of the observer, and the small distance between your eyes was enough to shift the thumb's apparent position. Now imagine trying to detect that same apparent jump, not for a thumb at arm's length, but for 100s of miles away. The shift would become so small that no human eye could hope to notice it. It would almost disappear. That vanishingly tiny change in apparent position, measured for stars instead of thumbs, is the foundation of how astronomers map the Milky Way, and ultimately how they uncovered a black hole that never emitted a single photon of its own. The method is called parallax, and it remains the most direct way astronomers have of measuring distance across space. As Earth travels around the Sun, our viewpoint shifts from one side of its orbit to the other over 6 months, creating a baseline unimaginably larger than the distance between your eyes. A nearby star, viewed from those opposite positions, appears to slide ever so slightly against the much more distant stars behind it. Measure that tiny shift. Combine it with the known size of Earth's orbit, and simple geometry gives you the distance without needing to guess how luminous the star truly is or compare it with any other object. It is about as close as astronomy comes to laying a ruler across the galaxy. The difficulty is that even for the nearest stars beyond the Sun, the shift is astonishingly, almost unimaginably, small. To appreciate just how small, it helps to linger on the units for a moment. Astronomers measure these angles in arcseconds, and a single arcsecond is already an extraordinarily fine slice of the sky, just 1/3600th of a degree, while the full moon itself spans about half a degree. Even the nearest stars beyond the Sun shift by less than 1 arcsecond as Earth completes its yearly orbit. Gaia, the European spacecraft built to measure those shifts, was designed to do something far more demanding. For its brighter stars, it could determine positions to roughly 20 microarcseconds, where a microarcsecond is 1/1,000,000th of a single arcsecond. A precision that small has been compared to standing in Paris and measuring the width of a single human hair lying on the streets of New York. That is the level of precision astronomers finally brought to the sky. Gaia carried that almost impossible ruler to a quiet gravitational balance point about 1.5 million kilometers from Earth, roughly 4 times farther away than the Moon, where our planet would no longer interrupt its view of the stars. From there, over more than a decade, it carried out a task remarkable mostly for its patience. It observed nearly 2 billion stars, not once, but on average, dozens of times each, building an ever more precise record of where every one of them lay and exactly how each one moved across the sky, accumulating roughly 3 trillion individual measurements in the process. No human being will ever examine MOSTO, and this is where Gaia begins doing something that almost feels impossible. Month after month, year after year, it keeps returning to the same stars, measuring their positions again and again with extraordinary precision. Most drift quietly across the sky exactly as they should. A few do something different. They wander, not randomly, but in a tiny repeating pattern, as though something invisible keeps tugging them slightly off course. Think back to the person standing on smooth ice with a heavy bag swinging around them. The bag traces the larger circle, but the person never stays perfectly still. They slide in their own smaller loop around the shared center of mass. A star orbiting an unseen companion behaves exactly the same way. The black hole remains completely dark. The star gives it away by drawing a tiny orbit of its own across the sky. Gaia cannot see the black hole. It sees the fingerprint the black hole leaves behind. That was a remarkably different strategy from almost every successful black hole search before it. X-ray observatories waited for matter falling inward to heat up until it blazed across the galaxy. Radial velocity studies focused on one carefully chosen star at a time, looking for subtle changes in its motion. Gaia took a much broader view. It measured nearly 2 billion stars without asking which ones looked interesting first. Afterwards, astronomers searched through that immense catalog for the few whose paths refused to stay perfectly straight. If a star traced a repeating wobble while no visible companion was present, something massive had to be hiding there. I think that's one of the most beautiful parts of this story. Gaia was never built as a black hole hunter. Its primary job was simply to map the Milky Way more accurately than anyone had ever managed before. But once your measurements become precise enough, entirely new discoveries begin appearing almost on their own. Gaia BH1 emerged, not because someone pointed a telescope into darkness looking for black holes, but because one perfectly ordinary sun-like star refused to move the way gravity said it should unless something invisible was pulling on it. That's an idea worth lingering on. Dormant black holes are almost impossible to detect directly because, by definition, they emit essentially no light. So instead of looking for the black holes themselves, astronomers learned to watch the stars around them with enough precision that gravity became visible. Every improvement in astrometry shrinks another corner where hidden objects can remain unnoticed. Gaia transformed precision into an entirely new observing technique. Instead of asking what shines, it asks what pulls. Once that door opened, astronomers knew the catalog would contain more than one surprise. Nearly 2 billion stars meant nearly 2 billion chances for gravity to betray something unseen. Gaia BH1 was only the beginning. As researchers dug deeper into the same data, they uncovered another dormant black hole, and then another. The third one, announced in 2024, turned out to be unlike anything anyone expected. It was so massive that it immediately raised an uncomfortable question. Had our picture of how stellar black holes form been missing something important all along? Until then, the stellar mass black holes in our own galaxy had occupied a fairly familiar range. Most weighed around 10 times the mass of the Sunday. Gaia BH1 fit comfortably into that picture. Even Cygnus 10-1, one of the most famous black holes ever discovered, comes in at roughly 21 solar masses. That already seemed remarkably heavy. Then Gaia delivered a dormant black hole with a mass of about 33 suns. It did not simply extend the distribution. It landed far beyond where many astronomers expected the Milky Way should still be making stellar black holes. The object is known as Gaia BH3, and it outweighs the Sun by about 33 times. That number is easier to appreciate beside the black holes we've already met tonight. Gaia BH1 is about 10 solar masses. Cygnus X1 comes in at roughly 21. Gaia BH3 reaches 33, making it the most massive stellar black hole ever confirmed in the Milky Way. And despite that extraordinary mass, it revealed itself in exactly the same quiet way. Nothing glowing, nothing exploding. Just a companion star tracing a tiny orbit that should never have existed unless something dark and immensely heavy was pulling on it. That discovery also solved a puzzle that had been growing for years. Ever since gravitational wave observatories began catching black holes colliding across the distant universe, astronomers had noticed something strange. Many of those black holes weighed 30 solar masses or more. Yet inside the Milky Way, almost every stellar black hole we could study directly seemed much lighter. It wasn't clear whether our galaxy really lacked these heavy weights, or whether we simply hadn't found them yet. Gaia BH3 answered that question rather decisively. Objects this massive are here too. They had simply been hiding. Which immediately raises another question. How does a star leave behind a black hole that massive? At first glance, the answer seems obvious. Start with an even bigger star. But nature isn't quite that cooperative. Massive stars spend millions of years shedding material through powerful stellar winds. The larger the star, the more fiercely those winds strip away its outer layers. By the time the star finally collapses, much of the mass it was born with has already drifted back into space. Building a 33 solar mass black hole is therefore much harder than simply building a very massive star. The clue came not from the black hole itself, but from the star still orbiting it. Its spectrum showed that it is extremely metal-poor. In astronomy, metals means every element heavier than hydrogen and helium. Carbon, oxygen, iron, silicon, everything forged by earlier generations of stars. This companion contains less than 1% as much of those elements as the Sunday. That makes it an unusually ancient star, formed when the Milky Way was still chemically young. And because binary stars are born from the same cloud of gas, the star that eventually became Gaia BH1 must have shared that same composition. That detail changes almost everything. Heavy elements help drive stellar winds by absorbing light inside a star's atmosphere. Remove most of those elements, and the winds weaken dramatically. The star loses far less material over its lifetime. So when a very massive metal-poor star finally reaches the end of its life, far more of its original mass survives long enough to collapse. The result can be a black hole much heavier than one produced by an otherwise similar star rich in heavy elements. Gaia BH1 is one of the clearest nearby examples of that process ever found. There's another reason this discovery feels remarkable. Gaia BH1 is only about 2,000 light-years away. By the standards of the Milky Way, that's close. Our galaxy stretches roughly 100,000 light-years across. For all of recorded astronomy, observers looked toward the constellation Aquila and saw nothing more than an ordinary faint star. The black hole was there the entire time, quietly steering that star around an invisible orbit. Nothing about the sky hinted at its presence. It took measurements of astonishing precision before gravity itself finally gave away what light never could. By now, a pattern has probably started to emerge. None of these black holes suddenly appeared. They were always part of our neighborhood. What changed was our ability to notice them. Better instruments have not been filling the Milky Way with black holes. They have been stripping away our ignorance, one layer at a time. Gaia BH1 is simply the largest object that process has uncovered so far, and even it could only be found because a nearby star betrayed its gravity. That last detail hints at a much bigger limitation. Every black hole we've discussed tonight had something visible orbiting it. Remove the companion star, and the entire method falls apart. Yet the population estimates we explored earlier point to a very different galaxy. Most stellar black holes are expected to wander alone, with no bright partner announcing their existence. If one of those lonely objects happened to lie closer than Gaia BH1, we wouldn't see a wobble because there would be nothing there to wobble. So how do you search for something that leaves no light, no flare, and not even a companion star to betray it? One possible answer begins in a place almost anyone can find. Look toward Taurus on a clear winter evening, and you'll notice a broad V-shaped pattern marking the bull's face. That's the Hyades, the nearest open star cluster to the Sun, only about 150 light-years away. Its stars were born together hundreds of millions of years ago and have been traveling through the galaxy as a family ever since. In 2023, astronomers suggested that this familiar cluster might be hiding the closest black holes ever proposed, roughly 10 times nearer than the nearest one we've actually confirmed. The numbers are almost hard to believe. Gaia BH1 is about 1,560 light-years away. The Hyades are only 150. That's not a small improvement. It's an order of magnitude closer. Yet nobody has found a star in the cluster circling an invisible companion. There is no elegant little wobble like the one Gaia caught. No obvious orbit. No smoking gun. So why suspect black holes at all? Because this time, astronomers weren't looking at individual stars. They were looking at the cluster itself. A star cluster is constantly reshaping under its own gravity. Over millions of years, the heavier members gradually sink inward while lighter stars migrate outward or escape entirely. Add a few 10 solar mass black holes to the center, and the whole system evolves differently. The central region becomes more energetic. The cluster expands. Its stars end up distributed in a noticeably different way. The black holes remain invisible, but the cluster no longer behaves as though they aren't there. To test that idea, researchers built thousands of numerical models of the Hyades and let them evolve across roughly 650 million years. Some simulations began with no black holes at all. Others placed 2 or 3 at the cluster's center. Then came the comparison. Gaia had already measured the positions and motions of the real Hyades stars with extraordinary accuracy. Which simulated cluster actually resembled the one hanging in our sky today? The closest match wasn't the version without black holes. It was the one that quietly carried 2 or 3 invisible objects, each weighing roughly 10 suns, buried deep in its core. Unlike Gaia BH1, this isn't a direct detection. No one has watched a single star orbit an unseen companion and measured the mass hiding there. Instead, the evidence comes from the behavior of the cluster as a whole. When researchers compared different evolutionary models, the versions containing a few black holes reproduced today's Hyades slightly better than those without them. That's an important distinction. It makes black holes the leading explanation, not the only possible one. Even the authors emphasize that point. Their models without black holes weren't impossible. They simply didn't fit the observations quite as well. That kind of caution is familiar for a reason. We've already seen how convincing black hole candidates can disappear once better observations arrive. HR 6819 taught astronomers that lesson very publicly. So the Hyades study stops short of claiming a discovery. It argues that the evidence leans in one direction, and that direction happens to point toward hidden black holes in the nearest star cluster to the Sunday. It's a quieter conclusion than most headlines prefer, but science usually advances through conclusions exactly like this. One small detail makes the scene even more interesting. The bright orange star that catches your eye at the point of the Hyades isn't actually part of the cluster at all. It's Aldebaran, a foreground giant sitting much closer to Earth, only lined up with the cluster by chance. The Hyades themselves lie farther behind it. So the feature that dominates the view isn't really the object we're talking about. The possible black holes, if they're there, belong to the quieter stars in the background. That feels strangely appropriate for this entire story. Again and again, the obvious object turns out not to be the important one. The simulations contained another surprise as well. They continued to match the real Hyades even in runs where the black holes had already been ejected from the cluster. The only requirement was timing. The ejection had to happen within roughly the last 150 million years. That's recent enough that the cluster would still carry the gravitational imprint of having hosted them. In other words, the black holes might still be sitting near the cluster's center tonight. Or they may already be gone, leaving only the shape of the cluster behind as evidence they were ever there. Either possibility keeps them remarkably close to us. Whether they're still inside the Hyades or drifting nearby, they remain the closest black holes anyone has seriously proposed. But if they've already escaped, another question immediately follows. What throws a black hole out of the very cluster where it was born? And if it can happen here, how many solitary black holes are already wandering through the Milky Way with nothing left to reveal where they came from? The answer begins at the moment the black hole is born. Massive stars don't collapse quietly. They end their lives in supernova explosions, and those explosions are rarely perfectly symmetrical. If more material is blasted away in one direction than another, momentum has to balance. The newborn black hole recoils the opposite way, much like a canoe sliding backward when someone jumps from its bow. Astronomers call this a natal kick. Depending on how asymmetric the explosion is, that kick can send a black hole racing away at tens or even hundreds of kilometers per second. A natal kick changes the picture quite a bit. It's easy to imagine black holes remaining where their parent stars were born, tucked inside the same clusters that formed them. Many probably don't. The explosion that creates a black hole can also send it racing away, leaving its birthplace behind. Some escape their clusters almost immediately. Others are gradually thrown out through countless gravitational encounters over millions of years. Either way, a large fraction eventually ends up alone, moving through the galaxy with no obvious connection to where it began. That possibility wasn't unique to the Hyades. In fact, it's expected to be fairly common. Stars are born in clusters, but clusters don't last forever. They slowly disperse, and the black holes inside them don't necessarily stay together either. Some remain bound for a time. Others are kicked free and spend the rest of cosmic history crossing the Milky Way on their own. The clusters are only the beginning of the story. The galaxy itself becomes home. Now think back to the estimate we built earlier. Roughly 100 million stellar black holes may inhabit the Milky Way. If natal kicks and later ejections are as common as current models suggest, then most of those objects are probably traveling alone. No companion star tracing an orbit. No gas spiraling inward to shine in X-rays. No star cluster whose structure gives them away. Every detection method we followed tonight depends on a black hole disturbing something visible. A solitary black hole drifting through empty space may leave nothing visible to disturb at all. And they don't remain close to where they formed. A natal kick of 100 kilometers per second is enough to carry a black hole from Earth to the Moon in about an hour. Keep that speed for millions of years, and the distance becomes enormous. Over time, these objects spread throughout the disk of the Milky Way, crossing the same regions occupied by ordinary stars. There's no special reason our part of the galaxy should be different. If these wanderers are common, some of them should eventually pass through the solar neighborhood as well. Statistically, the nearest stellar black hole is likely to be one of these travelers, rather than one comfortably orbiting a bright companion. That's what makes them so frustrating to find. We're not talking about objects that are merely faint. A lone black hole produces essentially no light of its own. It has no solid surface to reflect starlight, and for a typical stellar mass black hole, the event horizon is only a few dozen kilometers across, tiny against the vastness of interstellar space. Point a telescope directly toward one, and in almost every case you'll simply record the ordinary stars lying far behind it. Nothing announces that the black hole is there. It isn't hiding behind darkness. It simply leaves almost nothing for us to see, which for a long time really did seem like the end of the road. An isolated black hole looked like one of those objects physics could predict with complete confidence, but astronomy might never actually find. No light, no companion star, nothing to betray its presence. It seemed destined to remain a permanent blank spot in our census of the Milky Way. Yet even perfect darkness has one weakness. A black hole cannot stop having mass. And according to Einstein, mass doesn't simply pull on things. It changes the geometry of space itself. Light passing through that curved geometry has no choice but to follow the bend. So if a lone black hole drifts almost perfectly between us and a much more distant star, it briefly reveals itself in the only way it can, not by emitting light, but by distorting someone else's. That's exactly how astronomers finally caught one. In 2011, a star toward the crowded center of the Milky Way slowly brightened, remained unusually bright for many months, and then gradually faded again over roughly 270 days. Nothing had changed inside the star itself. Something dark had crossed in front of it. Long after the brightening ended, the Hubble Space Telescope continued watching the same field, measuring an almost impossibly small shift in the star's apparent position, the tiny deflection produced as its light curved around an unseen mass. Years of analysis eventually converged on a remarkable conclusion. The invisible lens was a black hole of roughly 7 solar masses, emitting no detectable light, orbiting no companion star, the first genuinely isolated black hole ever confirmed. It was also moving through the Milky Way at about 45 kilometers per second, almost exactly the kind of speed a natal kick could produce, a solitary traveler still carrying the momentum of its violent birth. The discovery was extraordinary, but it also showed just how difficult this path really is. Everything depended on a coincidence nobody could have planned. The black hole happened to pass almost perfectly across our line of sight to a distant star. Miss that alignment by a tiny amount, and nothing unusual would have appeared at all. Even with the event in hand, astronomers spent more than a decade refining the measurements, debating the interpretation, and carefully testing alternative explanations before the picture became convincing. One isolated black hole, discovered almost by accident, out of the 100 million we think may exist throughout the galaxy. If that much effort was needed to identify a single wanderer thousands of light years away, what chance do we have of finding the one statistics suggest may already be drifting somewhere much closer to home? The answer begins with one of Einstein's strangest ideas. Every object with mass reshapes the space around it. Your body does it. The Earth does it. The Sun does it far more strongly. A stellar black hole compresses the same effect into an extraordinarily small region of space. That is the one thing it can never hide. Even if it emits no light whatsoever, the geometry around it is no longer the same as empty space. Learning to detect that subtle distortion has become one of astronomy's most powerful ways of studying objects that are otherwise completely invisible. In Einstein's view, gravity isn't a mysterious force reaching across empty space. Space itself is curved by mass, and light simply follows the straightest path available through that curved landscape. Imagine rolling a marble across a stretched sheet. If the sheet dips, the marble changes direction without anything ever touching it. Light behaves in much the same way. As it passes close to a massive object, its path bends with the curvature of space, reaching us from a slightly different direction than it would have in perfectly empty space. Now imagine a black hole slowly drifting across that line of sight. The black hole itself remains completely invisible, but its gravity bends the light arriving from the distant star behind it. If the alignment is close enough, that bending becomes much more than a slight deflection. Gravity gathers the starlight and focuses it toward us, behaving like a lens made from space itself. The background star suddenly appears brighter, sometimes dramatically so, not because the star changed, but because an unseen object redirected more of its light toward Earth. Astronomers call this gravitational microlensing. It asks almost nothing of the black hole. No accretion disk, no companion star, no radiation. Only mass and a moment of almost perfect alignment. That alignment is both the strength of the method and its greatest limitation. A black hole has to pass almost exactly in front of a distant star from our point of view, not merely nearby, almost perfectly across the same line of sight. The Milky Way contains hundreds of billions of stars, yet it is also unimaginably empty. Most isolated black holes spend their entire existence crossing sight lines that lead nowhere at all. Millions of years can pass without a single useful alignment. Then, purely by chance, one drifts across the light of a distant star for a few months, and for that brief moment, gravity reveals what light never could. We can't predict when those moments will happen. The only strategy is patience. Watch millions of stars, year after year, and wait for one of them to brighten in exactly the right way. Catching the brief flash is only the beginning. Interpreting it is an entirely different challenge. At first glance, the brightening caused by gravitational microlensing can look surprisingly similar to the natural variability of certain stars. Brightness alone isn't enough to identify a black hole. Astronomers have to measure something even subtler. As the invisible lens moves across the line of sight, it doesn't just magnify the background star. It shifts the star's apparent position ever so slightly across the sky. The light isn't only brightened, its path is bent. The displacement is astonishingly small, completely invisible to the eye, and only detectable through years of exquisitely precise measurements from observatories like Hubble. The first isolated black hole ever confirmed shows just how demanding that process can be. The lensing event itself unfolded over roughly 270 days in 2011 as the unseen object drifted across the face of a distant star near the center of the Milky Way. That was only the opening chapter. The real work lasted for years. Astronomers followed the background star with Hubble, measuring its position again and again as it crept sideways by an almost immeasurable amount. Different research teams analyzed the same event, compared methods, questioned assumptions, and arrived at somewhat different estimates for the lensing object's mass before the evidence gradually converged. The final answer still carried honest uncertainty. Most likely, the object weighs around 7 times the mass of the Sun, comfortably within the range expected for a stellar black hole, but every decimal place was earned the hard way. That story says as much about our methods as it does about the black hole itself. Gravitational microlensing is the only technique capable of revealing a truly isolated black hole, yet it depends on a coincidence we cannot predict and cannot repeat. Even when nature gives us that opportunity, years of patient analysis are needed before we know what we've actually found. It's a remarkable tool, but not a practical census. It cannot survey the space around the Sun and tell us what is hiding nearby. It can only wait for rare alignments, one after another, scattered unpredictably across the sky. Every confirmed isolated black hole is therefore likely to be an exception, a fortunate event caught at exactly the right moment rather than part of a complete map of our neighborhood. Now, think again about the black hole statistics we've been building throughout tonight. If the nearest one happens to be traveling alone and current models suggest that's the most likely case, then Gaia won't find it because there is no companion star to wobble. X-ray telescopes won't find it because there is no gas falling inward to shine. Star cluster dynamics won't reveal it because it belongs to no cluster at all. Its only realistic chance of discovery is to wander, someday, almost perfectly across the light of a distant background star. And even then, we would have to be watching that exact star at that exact time. It's entirely possible that the nearest black hole has already spent thousands of years passing quietly through our galactic neighborhood without producing a single observable clue. By this point, the individual pieces have started fitting together on their own. Around 100 million stellar black holes scattered throughout the Milky Way. The nearest confirmed example still more than 1,500 light-years away because it happened to keep a visible companion. Population estimates pointing toward another object much closer, but traveling alone. A detection method for isolated black holes that succeeds only through extraordinarily rare alignments and years of painstaking analysis. None of those facts contradict one another. In fact, they point toward the same conclusion with surprising consistency. It is a conclusion no single telescope has observed directly, yet one that follows naturally from everything we've learned. The nearest black hole to Earth is almost certainly not Gaia BH1. It isn't Gaia BH3. It isn't any object with a catalog number or a well-measured orbit. The closest black hole is almost certainly one we have never detected at all. We don't know where it is. We don't know what direction to point a telescope. We may not even discover it within our lifetimes. Yet the evidence we've followed tonight suggests something difficult to ignore. Somewhere in the vast but surprisingly local volume of space around the Sun, an unseen black hole has almost certainly been drifting through the darkness for all of human history, waiting for a moment when gravity, rather than light, finally gives it away. Before we go any further, it's worth putting the evidence together carefully, because none of what follows depends on speculation. We know the Milky Way should contain roughly 100 million stellar black holes. That estimate comes directly from how massive stars are born, evolve, and die. Most of those black holes have never been observed, but their existence is an expected consequence of well-tested stellar evolution. We also know they should be distributed throughout the galactic disk in broadly the same regions where their parent stars once lived. At that average density, simple statistics suggest that one should lie within roughly 50 light-years of the Sunday. We know most stellar black holes probably travel alone because the explosions that create them often disrupt binary systems or eject the remnants entirely. And we know that an isolated black hole leaves almost nothing for us to detect unless, by extraordinary coincidence, it drifts across the light of a distant background star. None of those ideas sits at the edge of astronomy. They are all ordinary pieces of modern astrophysics. The surprise only appears when they are placed beside one another. The distance between what we have confirmed and what almost certainly exists is enormous. The nearest confirmed stellar black hole, Gaia BH1, lies about 1,560 light-years away. Population statistics suggest that the true nearest one is likely to be somewhere within roughly 50 light-years. That's a difference of about 30 in distance. In three-dimensional space, it means searching a volume tens of thousands of times smaller. Imagine believing the nearest person to you was 30 miles away. You would naturally picture yourself surrounded by empty space. Then imagine discovering that someone had almost certainly been standing only a mile away the entire time, perfectly silent, invisible in the darkness, leaving no sound, no light, no obvious trace of their presence. The world itself hasn't changed. Only your understanding of it has. That distinction matters more than it first appears. The nearest black hole didn't suddenly move closer because astronomers improved their calculations. It didn't quietly drift into the solar neighborhood sometime during recorded history. Whatever object holds that title has almost certainly occupied this region of the galaxy for millions of years, long before there were human beings to wonder whether black holes even existed. Every generation that looked up at the night sky did so beneath the influence of the same invisible neighbor. The astronomers who traced the Hyades across winter evenings were living beside it. The civilizations that named Orion and Taurus shared the sky with it as well. Nothing in the heavens changed when we reached this conclusion. What changed was our ability to recognize that the sky had always contained more than we could see. That realization carries an unusual kind of discomfort. It isn't the discomfort of immediate danger. We'll come back to that question shortly. It's something quieter than fear. It's the feeling of discovering that a map you believed was nearly complete has always contained an empty space that cannot simply be filled in. For centuries, it was tempting to imagine that our stellar neighborhood could eventually be cataloged in its entirety. Every nearby star identified. Every neighboring system given a name and a distance. Isolated black holes quietly undermine that picture. They remind us that part of our own galactic neighborhood may remain fundamentally anonymous. Not because we've failed to search carefully enough, but because nature has produced objects that leave almost no observable signature at all. That's why this unknown feels different from so many others in science. Most unknowns are simply problems waiting for better instruments. Build a larger telescope, collect more data, and eventually the uncertainty begins to disappear. To some extent, that will happen here as well. Future observatories will almost certainly discover many more isolated black holes than we know today. But the single nearest one may remain an exception. Identifying it depends on a chance alignment that could easily fail to occur during our lifetimes, or during many generations after us. That leaves astronomy in an unusual position. We can be remarkably confident that the object exists. We can estimate roughly how far away it is. We understand how it formed and why it hides so effectively. And yet we may never know where, exactly, to point a telescope to see it. If there's anything reassuring in all of this, it isn't that we've found the nearest black hole. We almost certainly haven't. It's that we've learned so much about something we may never see directly. We can estimate its likely mass. We can estimate how far away it probably is. We understand how it was born in the collapse of a massive star, why it almost certainly travels alone, and why it hides so effectively from every telescope we build. None of that came from seeing the object itself. It came from understanding the rules the universe follows. Piece by piece, those rules let us describe something that remains completely invisible. Even so, one question naturally refuses to go away. If an unseen black hole is probably wandering somewhere in our cosmic neighborhood, perhaps even closer than the nearest named star, what would that actually mean for us? Distance is one thing. Consequence is another. Would we notice if such an object were slowly approaching the solar system? Could it arrive without warning? The first part of the answer sounds unsettling until you put it into context. Our solar system is not isolated. Stars pass through our broader neighborhood all the time. On average, around 10 stars move through the outer reaches of the solar system every million years. That traffic has been continuing since the Sun first formed more than 4.5 billion years ago. Space feels empty because everything moves so slowly across such enormous distances. But on galactic timescales, our neighborhood is anything but still. We know this isn't just a statistical prediction because one of those close passages happened recently enough that our own species was already here to witness it. About 70,000 years ago, a faint red dwarf and its brown dwarf companion, together known as Schultz's star, passed within roughly 52,000 astronomical units of the Sunday. That's about 8/10 of a light year. Measured against everyday experience, it sounds unimaginably far away. Measured against the 1,500 light-year distance to Gaia BH1, it was astonishingly close. The system appears to have skimmed through the outer edge of the Oort cloud, the immense reservoir of icy bodies surrounding the solar system far beyond the planets. Human beings were already walking the Earth. On exceptionally dark nights, some of them may even have seen the star itself without realizing just how close it had come. The remarkable part is what happened next. Almost nothing. Schultz's star slipped through the outer Oort cloud without disturbing life on Earth in any noticeable way. Its gravity was simply too weak at that distance to do much more than gently alter the paths of a small number of distant comets. Even those tiny gravitational nudges don't produce immediate consequences. If a comet is sent inward at all, the journey toward the inner solar system typically takes on the order of 2 million years. A star passed closer than any black hole we've ever confirmed, close enough that humans were alive to witness the encounter, and the solar system barely noticed. The same perspective applies to a wandering black hole. A 10 solar mass black hole is certainly more massive than Schultz's star, but a distant flyby would follow the same basic physics. Gravity weakens rapidly with distance, and the distances involved remain immense. An approaching black hole wouldn't suddenly appear in the night sky. It wouldn't rush toward us over the course of months or even centuries. Traveling at a typical speed through the Milky Way, an object starting roughly a light year away would require many thousands of years to cover that distance. Any close approach would unfold so gradually that countless generations of human beings could be born, live their entire lives, and disappear before the encounter had even reached its closest point. But suppose one really were out there, moving slowly toward the solar system through the darkness. Would we know? The answer brings us back to the same problem we've been circling all night. A dormant black hole traveling alone has almost nothing visible to announce its approach. If it carried a companion star, we would discover the companion long before the black hole itself became important. If it were actively feeding, its accretion disk would shine in X-rays. But an isolated black hole crossing interstellar space offers neither clue. The first evidence wouldn't come from the black hole directly. It would come from gravity. Long before the object reached the inner solar system, its pull would begin ever so slightly reshaping the orbits of the most distant bodies in the Oort cloud. The signal would resemble the gravitational fingerprints left by passing stars like Schultz's star, except this time, we would be watching the disturbance unfold instead of reconstructing it after the fact. Once again, we would infer the object before we ever saw it, not from its light, but from the way its gravity quietly altered everything around it. The architecture of the solar system gives us far more warning than intuition suggests. The Oort cloud extends outward for something like 100,000 times the distance between Earth and the Sun, forming an enormous, diffuse halo that marks the outer frontier of the Sun's gravitational influence. Any wandering object approaching from interstellar space has to cross that immense region first. Long before it came anywhere near the planets, it would begin gently disturbing the orbits of distant comets scattered throughout the cloud. The planets occupy only a tiny central region buried deep inside this vast structure. For a black hole to pose a direct threat to Earth, it would have to travel through nearly the entire Oort cloud and then pass extraordinarily close to the Sun itself. In astronomical terms, that's less like wandering into a neighborhood and more like throwing a dart across an ocean and striking a single grain of sand. Almost every plausible encounter would be nothing more than a distant flyby, much like the one humanity unknowingly experienced with Schultz's star. This is one of those situations where the numbers are more reassuring than intuition. Instinct treats an unseen black hole as something waiting in the darkness. Physics describes something very different. A black hole crossing the galaxy is simply another star-sized mass moving through an almost incomprehensibly empty volume of space. The overwhelming majority never come remotely close to us. Those that do pass nearby move on timescales measured in thousands, often tens of thousands, of years. And long before such an object could influence the inner solar system in any meaningful way, its gravity would already be leaving detectable signatures among the distant bodies at its edge. In the end, the same emptiness that makes black holes so difficult to discover is also what makes truly dangerous encounters extraordinarily unlikely. We often talk about black holes as though they possess a special kind of gravity, something uniquely violent that ordinary stars simply don't have. It's built into the language itself. We say they swallow. They devour. They suck everything toward them. Those words create an image that is far more dramatic than the underlying physics. A black hole doesn't produce a mysterious new form of gravity. From a distance, it pulls exactly as strongly as any other object with the same mass. No more. No less. That's easier to see with a thought experiment. Imagine replacing the Sun, this very instant, with a black hole of exactly one solar mass. Nothing else changes. The mass remains identical. Earth wouldn't suddenly spiral inward. It wouldn't be swallowed. It would continue following essentially the same orbit it follows today, because from Earth's distance, the gravitational field would be unchanged. The solar system would become unimaginably cold and completely dark, but it wouldn't immediately collapse into the black hole. Gravity, at that distance, would still be doing exactly what it has always done. The explanation turns out to be remarkably simple. Gravity depends on only two things: mass and distance. Nothing else enters the calculation. It doesn't matter whether the object is glowing or completely dark. It doesn't matter whether the mass is spread across a huge star or compressed into a black hole. If two objects contain the same mass and you're the same distance from both, their gravitational pull is exactly the same. A 10 solar mass star and a 10 solar mass black hole exert identical gravity from the same distance. The difference only appears when you move extraordinarily close. That's where a black hole becomes something entirely different. We can put numbers to that. Imagine a black hole containing 10 times the mass of the Sun, sitting 1 light-year away. Actually farther than population statistics suggest the nearest one is likely to be, but still comfortably nearby on galactic scales. A light-year is about 9.5 trillion kilometers. It's an almost impossible distance to picture. Yet if you calculate the gravitational pull that black hole exerts on your body as you lie in bed tonight, the result is astonishing. It's weaker than the pull from an ordinary delivery truck parked across the street. The comparison feels absurd until you remember how gravity works. The truck may weigh only a few tons, but it's perhaps 10 meters away. The black hole weighs 10 suns, yet it's separated from you by nearly 6 trillion miles. Distance overwhelms mass. Every time. That's the part hidden by the phrase, black holes suck everything in. Gravity doesn't simply become weaker with distance. It weakens with the square of the distance. Double the distance, and the pull falls to 1/4. Triple it, and only 1/9 remains. Stretch that separation to an entire light year, and even an object weighing many suns becomes almost irrelevant to your everyday life. From where you're lying, the walls around you exert a stronger gravitational pull. So does the mattress beneath you. If someone is asleep beside you, their gravity matters more as well. Darkness doesn't give gravity a longer reach. The universe makes no distinction between visible mass and invisible mass. So why are black holes genuinely dangerous at all? Not because they pull harder across interstellar space. They don't. The danger begins only when you get extraordinarily close. A normal star has a surface. If you fall toward the sun, its outer layers stop your journey while you're still almost 700,000 kilometers from its center. Gravity is almostly intense there, but there is still something to collide with before you ever reach the mass concentrated inside. A black hole offers no such barrier. Those same 10 solar masses are compressed into a region only about 60 kilometers across. Nothing prevents you from falling closer and closer to that concentration of mass. And every step inward makes gravity dramatically stronger than it was the step before. The danger isn't how far a black hole reaches. It's how close nature allows you to get. Imagine two depressions in the ground containing the same total amount of depth. One is a broad, gently sloping bowl. The other is a narrow well descending almost straight downward. Roll a marble past either one from far away, and both deflect its path by almost exactly the same amount, because both contain the same overall mass. Only when the marble reaches the center does the difference become obvious. The bowl eventually gives it a surface to rest on. The well never does. That's the difference between a star and a black hole. Not a stronger pull across the galaxy, but a far steeper landscape once you arrive at the very center. Looking back, that changes the emotional shape of this entire journey. We began with the unsettling possibility that the nearest black hole may be far closer than any object we've actually identified. On its own, that sounds deeply unsettling. But the same physics that hides these objects also protects us from them. Space is unimaginably large. Gravity weakens relentlessly with distance. The nearest black hole may well be closer than the nearest named star, yet still exert less influence on your body than the furniture surrounding you at this moment. It isn't waiting in the darkness like a predator. It's simply another mass moving quietly through the Milky Way, following the same laws of gravity that have guided every planet, every star, and every galaxy since the universe began. That leaves us with a question that has almost nothing to do with astronomy. If a black hole at any realistic distance is this harmless, this weak in its influence, this completely indifferent to us, why does the thought of one nearby still feel so heavy? Why can an invisible object a light year away, pulling on your body less strongly than a truck across the street, create an unease that the truck never could? The danger may be negligible, but the feeling is not. And the reason has less to do with black holes than with the minds considering them. minds shaped long before anyone knew that black holes existed. A truck parked outside and a black hole drifting a light year away are not even close in their gravitational effect on you. The truck matters more. Yet no one lies awake thinking about the silent mass of a vehicle across the street. The black hole is different. Even after the numbers have made it harmless, the idea catches somewhere deeper and stays there. That reaction is not stupidity, and it is not evidence that the physics has failed to reassure us. It is an older system, responding exactly as it was built to respond. Only now it is facing a situation so far outside its original world that the response no longer fits the threat. The fear is genuine. Its target is simply unfamiliar. For most of human existence, the most dangerous things were often the things that could not be seen clearly. A predator hidden in tall grass. A rival waiting beyond a ridge. A snake moving somewhere outside the firelight. A visible danger could at least be tracked. Distance could be judged. Escape could begin. The unseen threat offered none of that. It could already be close. It could already be moving. By the time it became visible, the moment to react might have passed. So caution around darkness was not a weakness. It was useful. The people whose minds filled an empty-looking night with possible danger were often the people who survived it. That vigilance never disappeared. A hidden black hole activates many of the same signals our ancestors once relied on. It cannot be seen, so it cannot be watched. It is powerful, so the mind assigns it the ability to destroy. It is somewhere nearby, but its location is unknown. Invisible. Powerful. Unlocated. To an ancient nervous system, that combination looks less like an astronomical object and more like something waiting beyond the grass. The mind does not pause to calculate how gravity falls with the square of distance. It does not compare the pull of 10 suns across a light year with the pull of a truck 10 meters away. It hears hidden, powerful, and close, then sounds the same alarm that once kept a vulnerable body alive in the dark. The alarm is not malfunctioning. It is working with measurements it was never designed to understand. Human intuition was shaped around distances that could be crossed on foot, threats that could be touched, and changes that unfolded within a lifetime. It has no natural scale for a light year. Even Gaia BH1, the nearest confirmed black hole, lies about 1,560 light-years away. That places it roughly 40 billion times farther from your bed than the moon. 40 billion is a number the mind can repeat, but not one it can honestly feel. So when the words black hole and nearby appear together, nearby wins. The body responds to the familiar meaning of the word before the true distance has any chance to become real. That is why reassurance by itself rarely works. Being told not to worry does not quiet a system that was never built to obey language. The alarm is older than argument. But distances can be compared. Forces can be calculated. The empty space between worlds can be measured. And once the numbers are allowed to accumulate, the feeling begins to change. Not because the fear has been dismissed, but because it has finally been given the scale it was missing. A predator near the edge of a fire is close in the way the body understands closeness. A black hole, a light year away, is close only by the standards of a galaxy. Between those two meanings lies nearly 10 trillion kilometers. The ancient alarm may still ring. Understanding does not erase it completely. What understanding can do is change what the alarm means. It can separate presence from danger. It can distinguish something hidden nearby from something capable of reaching us. The mind once treated fear as information because, in the world where that response evolved, it often was. A sound beyond the fire might mean movement. Movement might mean a predator. Hesitation might cost a life. But the universe is larger than the world that trained those instincts. Understanding is how the old information gets revised when the scale changes. There is something deeply human in the fact that both systems remain active at once. The same mind that can infer the mass of an invisible black hole from the tiny motion of a distant star can still tense at the thought of something unseen in the darkness. One part of us measures stellar orbits, bends light through equations, and reconstructs the depths of stars that vanished millions of years ago. Another part listens for movement beyond the edge of the room. One reaches across 1,500 light-years with mathematics. The other still watches the shadows. Neither response makes the other less real. They belong to the same animal, the ancient caution and the patient intellect, sharing one quiet body beneath one dark ceiling. Once you understand where that fear comes from, it becomes easier to hold. The alarm itself is not your enemy. It kept your ancestors alive through countless nights when the darkness really did contain teeth, claws, and movement just beyond the fire. It worked well enough, for long enough, that their lives eventually led to yours, to this quiet moment when you can lie safely in bed and wonder about black holes instead of listening for predators. That vigilance was carried forward through generation after generation because, for most of human history, it was useful. Tonight, it is simply responding to the wrong scale, treating a distant and almost powerless mass as though it were something close enough to strike. The alarm can be heard without being followed. It has done what it was built to do. The physics can take over from here. But one discomfort remains, and it comes from somewhere deeper than fear. It comes from the possibility that knowledge itself may reach a boundary. So far, every invisible black hole in this story has carried at least some promise of discovery. A hidden companion might reveal itself through the motion of a star. A solitary wanderer might cross the light of something farther away. In principle, patience and better instruments could eventually expose them. But some black holes may offer no such opportunity. They may sit nearby without producing any signal that our telescopes can reliably separate from the surrounding darkness. The nearest black hole may not simply be missing from the catalog. It may belong to a class of objects that no realistic search could ever locate. Until now, the phrase "cannot see" has quietly carried the word "yet" behind it. We cannot see dormant black holes yet, but stellar wobbles are beginning to reveal them. We cannot see isolated wanderers yet, but microlensing can sometimes expose their gravity. The hidden population seems difficult, rather than unreachable, waiting for larger surveys, longer observations, and more precise measurements. That expectation has shaped nearly every discovery in modern astronomy. What is invisible today becomes measurable tomorrow. But not every absence is temporary. Some black holes may remain hidden not because our technology is still young, but because the objects themselves provide almost nothing for technology to measure. And the closest one to Earth could be among them. Imagine a completely isolated black hole drifting 10 light-years from the Sun. It emits no light, so no ordinary telescope can photograph it. It has no companion, so there is no nearby star tracing an orbit around an invisible mass. It is not consuming gas from a neighboring star, so there is no bright accretion disk and no burst of X-rays. Almost every method that found the black holes in this story disappears at once. What remains is gravitational microlensing, the rare moment when the black hole passes almost perfectly in front of a distant background star and bends that star's light toward us. But the geometry has to be extraordinarily precise. The black hole, the background star, and Earth must align closely enough for the effect to become measurable from our exact position in space. A black hole only 10 light-years away could drift across the sky for tens of thousands of years without passing in front of a suitable star, or without producing an alignment during any period of time that human observers could realistically wait through. The one technique capable of exposing an isolated black hole may simply never receive the geometry it needs. There is another possible signal, although it is even more difficult to use. Interstellar space is not perfectly empty. A thin scattering of gas exists between the stars, and a black hole moving through that gas should capture a small fraction of it. As the material falls inward, it accelerates, heats, and may release a faint trace of radiation. In principle, even a solitary black hole could therefore produce some light. In practice, the gas surrounding the solar neighborhood is so diffuse that very little matter would ever reach the black hole. The resulting emission could be billions of times dimmer than the faintest ordinary stars in existing catalogs. Detecting it would require an instrument far more sensitive than anything available today, aimed at exactly the correct patch of apparently empty sky, with no visible clue telling astronomers where that patch should be. The radiation may exist. It may still be too faint to distinguish from the darkness around it. That places astronomy in an unusual position. Most scientific limits invite an obvious response. Build a larger telescope. Observe for longer. Survey more of the sky. Measure with greater precision. Those improvements will reveal many more black holes. New wide-field surveys will repeatedly scan enormous regions of the sky and capture microlensing events that earlier searches would have missed. Gaia's later data releases should expose additional dormant black holes through the motions of their visible companions. The known population will grow. The statistics will improve. Entire categories of hidden objects will become less hidden than they are today. But none of that guarantees the discovery of the nearest black hole. If it travels alone, consumes almost nothing, and never crosses the light of a suitable background star, it could remain absent from every future catalog. Not because astronomers overlooked it, but because it never presents them with anything they can observe. I want to be careful about what this claim actually means. It is not that the nearest black hole can never be found, or that some law of physics prevents us from discovering it. We could get lucky next year. Future instruments may reveal something today's telescopes simply cannot. The point is more subtle than that. Right now, we have good reason to believe a nearby black hole exists, and we can estimate the kind of object it is and roughly how close it should be. What we do not know is whether ordinary observations will ever be enough to identify it directly. That uncertainty may stay with us for a very long time. At first, that feels disappointing. It is natural to see an empty place on the map as something unfinished. But the picture is more interesting than an empty space suggests. We already understand a surprising amount about the object we are looking for. It is almost certainly the remnant of a massive star. We have good estimates for the range of masses such an object should have, how it ended up in our part of the galaxy, and why it gives off almost no light of its own. What is missing is not the story. It is the address. That is a strange kind of knowledge. We can describe the object with growing confidence while still being unable to point to it in the sky. I find that limit surprisingly satisfying. It reminds us that understanding and possession are not the same thing. We often imagine that knowing something means being able to locate it, photograph it, or measure it directly. Science is not always that tidy. Sometimes we understand an object because every piece of evidence points toward what it must be, even if the object itself stays hidden. The nearest black hole may be one of those cases. There is something quietly reassuring about that. The universe does not have to reveal everything for us to learn something real about it. That brings us to one last possibility. Everything we have talked about tonight assumes these nearby black holes formed the familiar way when massive stars collapsed at the end of their lives. That is the only origin we have confirmed through observation. But there is another idea, much older and far more speculative. It suggests that some black holes may have formed long before the first stars ever existed. If they are real, they could be much smaller than any black hole produced by stellar collapse. And if even one survived nearby, it would force us to rethink what the nearest black hole really means. Every confirmed black hole we know today traces back to the same basic story. A massive star exhausted its fuel, gravity took over, and the collapsing core became a black hole. Every observation so far fits that picture. Yet physics leaves open another possibility. Black holes may not need stars at all. Under the right conditions, they could have formed when the universe itself was only moments old. If that happened, some of them might be astonishingly small, far smaller than anything stellar collapse can produce. To understand that idea, we have to go back almost to the beginning. During the first tiny fraction of a second after the Big Bang, the universe was extraordinarily smooth, though never perfectly so. Small fluctuations in density were already present, leaving some regions just a little denser than their surroundings. Most of those fluctuations eventually became the seeds of galaxies. But theorists have suggested that a few rare patches may have been dense enough for gravity to overwhelm everything else immediately. Instead of expanding with the rest of the young universe, those regions could have collapsed straight into black holes before the first stars, galaxies, or even atoms had fully formed. These hypothetical objects are known as primordial black holes. Unlike black holes born from dying stars, they are not tied to the mass of any stellar ancestor. In principle, they could exist across an enormous range of sizes, including masses no collapsing star could ever produce. That freedom in mass is what makes primordial black holes so unusual. A black hole formed from a dying star cannot be arbitrarily small. The collapsing core needs enough mass, at least about 3 suns worth, for gravity to overcome every known force resisting collapse. Primordial black holes are different. If they formed in the early universe, their masses would depend on the conditions at the moment they were born, not on the life of a star. In principle, one could weigh as much as a mountain, another as much as an asteroid, and others could fall somewhere in between. Imagine one with 5 times Earth's mass. Its event horizon, the surface beyond which nothing can escape, would be only about 10 centimeters across, roughly the size of a grapefruit. 5 Earths of mass compressed into something that could rest in your hands, emitting almost no light, drifting quietly through space. That picture sounds almost unbelievable, but it has appeared in serious scientific work. Astronomers have spent years studying a small group of icy objects far beyond Neptune whose orbits seem to share an unexpected pattern. One possible explanation is that a massive unseen object is shaping those orbits through its gravity. The leading idea is Planet 9, an undiscovered planet perhaps several times more massive than Earth, orbiting hundreds of astronomical units from the Sunday. a few researchers have suggested another possibility. Instead of a planet, the unseen object could be a primordial black hole with roughly 5 to 10 Earth masses, captured by the solar system long ago. From gravity alone, those two possibilities would behave almost identically. A planet and a black hole with the same mass pull on surrounding objects in exactly the same way. The distant icy bodies would not reveal which one was actually there. It is important to keep that idea in perspective. There is no evidence that Planet 9 is a black hole. In fact, there is still no direct evidence that Planet 9 exists at all. The case begins with a handful of unusual orbits, and even those may eventually prove to have a different explanation. The primordial black hole scenario goes one step further, building an additional hypothesis on top of an already uncertain one. No one is claiming that our solar system contains a hidden black hole. The interesting point is simply this. If a small primordial black hole were orbiting far beyond Neptune, most of our instruments would not see it directly. We would notice only its gravity, much as we have throughout this story whenever darkness revealed itself by the motion of something else. If primordial black holes exist, they also touch one of the biggest unanswered questions in modern cosmology. Most of the matter in the universe cannot be seen. Galaxies rotate too quickly to be held together by the gravity of their visible stars alone, implying the presence of a great deal of unseen mass. Whatever that dark matter is, no experiment has yet identified it. One long-standing possibility is that at least some of it consists of primordial black holes formed in the early universe. Over the years, astronomers have tested that idea in many different ways, and those searches have ruled out large portions of the allowed mass range. Even so, the idea has not disappeared completely. Some windows remain open, leaving room for the possibility that a fraction of dark matter is made of black holes older than the first stars. That possibility changes the question we started with in a subtle way. Tonight we have been asking how close the nearest stellar black hole might be, and the answer turned out to be much closer than the nearest one we have actually identified. But stellar black holes may not be the whole story. If primordial black holes exist and are scattered throughout the galaxy, then the nearest black hole of any kind might not be the remnant of a dead star at all. It could be something far older, far smaller, and potentially much closer than 50 light-years. That remains speculation rather than observation. Still, it carries the central idea of this journey one step further. The unseen universe may be closer than we imagine. Some of it may also be older than the stars themselves. Whether or not primordial black holes exist, the story does not end here. The Milky Way is still creating new black holes as massive stars reach the ends of their lives, and it will continue doing so long after humanity is gone. The map we have been building tonight is not permanent. It captures the galaxy as it happens to be today, even though that picture has been changing for billions of years and will keep changing for billions more. So what happens if we let time run forward? Across the long future of the Milky Way, could one of these dark wanderers ever come close enough to matter? Everything on our map is moving. Nearby stars drift through space. Black holes follow their own orbits around the galaxy. The Milky Way itself rotates, carrying the Sun around its center roughly once every 230 million years. Since complex life first appeared on Earth, our solar system has completed only a handful of those enormous journeys. So, when we say a black hole lies within 50 light-years today, we are describing only the present arrangement. Given enough time, every neighborhood in the galaxy changes. Stars move away. Others drift in. Black holes do the same. That changing picture is constantly being replenished. Somewhere in the Milky Way, another massive star eventually exhausts its fuel and collapses. On average, astronomers estimate that our galaxy forms roughly one new stellar black hole every century, though the exact rate is uncertain. A century feels long to us, but it is barely a moment on galactic timescales. Since the first pyramids were built, dozens of new black holes have probably joined the population, each beginning its own slow journey through the galactic disk. The estimate of around 100 million stellar black holes is not a fixed count. It is still growing, one dying massive star at a time. The black holes already in the galaxy are moving as well. Stars do not remain beside the same neighbors forever. Each follows its own orbit, with its own speed and direction, gradually reshaping the local stellar population over millions of years. The stars closest to the Sun today were not always our nearest neighbors, and they will not remain so indefinitely. Black holes are no different. Whatever object happens to be the nearest black hole today will eventually move elsewhere, while another takes its place. No human life is long enough to watch that exchange happen. But across the lifetime of the galaxy, it is completely ordinary. The nearest black hole is not a permanent title. It changes as the galaxy slowly rearranges itself. That naturally leads to the question we have been approaching all night. If black holes wander through the galaxy, could one eventually come close enough to affect the solar system? Not merely passing within a light year, as Schultz's star once did, but close enough to noticeably disturb the planets. Here, the enormous scale of the galaxy becomes reassuring. Encounters capable of seriously disrupting the inner solar system are extraordinarily rare. The stars are separated by immense distances compared with the speeds at which they move, making close encounters exceptionally uncommon. Most of the Milky Way is simply empty space. That emptiness is why stars and black holes almost always pass one another at safe distances. The timescales make the picture even clearer. Our Sun has roughly 5 billion years remaining before it expands into a red giant. During that entire period, the chance of a wandering black hole passing close enough to seriously alter Earth's orbit is extraordinarily small. Other long-term changes are overwhelmingly more certain. The Sun's gradual increase in brightness will make Earth uninhabitable long before a close black hole encounter becomes a realistic concern. Black holes are simply too sparse, and interstellar space is far too vast for such encounters to happen often. The nearest black hole is almost certainly closer than we once believed. Even so, every line of evidence says it will remain a distant neighbor for all the time that matters to us. And then the story stretches far beyond the lifetime of the Sunday. Long after the last stars have exhausted their fuel, black holes will remain. They are among the longest-lived objects the universe can produce. Even they are not eternal. Over unimaginable spans of time, they slowly lose energy through Hawking radiation and eventually disappear. But compared with every shining star, their lives are extraordinarily long. The distant future of the universe will not be defined by starlight. It will be a quieter place, where black holes drift through an increasingly dark cosmos after almost every source of light has gone. In that sense, the objects we struggle to detect today may become some of the last major structures the universe still contains. Seen from that perspective, a nearby black hole feels different. It is not an outsider interrupting a bright universe. It belongs to the same long story as everything else around us. We happen to live during the era when stars dominate the sky, but that era is only one chapter in cosmic history. Before it came a much darker universe. After it, another dark era is expected to follow. A black hole simply reminds us that those later chapters are already part of the universe we inhabit today. It has been here all along. We are only beginning to notice it. Across everything we have explored tonight, one fact stands out more than the black holes themselves. A species living on a small rocky planet has learned to detect objects that emit no light at all. We have estimated how many exist in our galaxy, measured their masses, reconstructed how they formed, and even begun asking where the unseen ones might be hiding. None of that required leaving the solar system. It came from careful observation, mathematics, and instruments built over generations. That may be the most remarkable part of this entire story. Before asking what black holes reveal about the universe, it is worth noticing what they reveal about the people determined to understand it. One lesson keeps returning throughout that effort. There is an important difference between something we have not yet discovered and something that may remain beyond our reach. Most scientific questions begin in the first category. Better observations gradually replace uncertainty with evidence. The search for the nearest black hole introduces a more difficult possibility. Some objects may exist, and we may understand their nature remarkably well, while still lacking any practical way to identify the specific object itself. Recognizing that limit is not a failure of science. It is part of doing science honestly. Knowing exactly where the evidence ends is often as important as knowing where it begins. That principle has appeared more than once in this story. When astronomers first announced a black hole in the HR 6819 system, other researchers revisited the evidence instead of accepting the result at face value. By carefully separating what the observations required from what they merely allowed, they eventually showed that two ordinary stars explained the data without a black hole. Something similar happened with the Hyades cluster. Simulations suggested that unseen black holes could explain its structure, but the researchers stopped short of calling it a detection because other explanations were still possible. In both cases, the strongest conclusions came from respecting the limits of the evidence rather than pushing beyond them. That habit of restraint is one of the reasons scientific knowledge becomes more reliable over time. This is a quieter kind of scientific rigor than people often imagine. Discovery is usually pictured as a series of breakthroughs, each one claiming another piece of unknown territory. In practice, science spends just as much effort defining where the evidence ends. A good map does more than show what is known. It also shows where confidence begins to fade. Leaving those boundaries out does not make the picture more complete. It only makes it less reliable. The most useful map separates established results from reasonable inference and from questions that remain unanswered. Everything we have discussed tonight depends on keeping those categories distinct instead of quietly blending them together. Look back at the claims we have made, and each falls into a different category. The Milky Way probably contains around 100 million stellar black holes. That estimate rests on well-understood models of how massive stars live and die. The idea that one of those black holes is likely to lie within about 50 light-years of the Sun is an inference based on those numbers and on the assumption that our local region of the galaxy is fairly typical. The suggestion that the nearest one may be an isolated black hole we never identify follows from the strengths and limitations of the methods available today. A nearby primordial black hole, on the other hand, belongs in a different category altogether. It remains an interesting possibility, but one without observational support. Keeping those levels of confidence separate is what makes the overall picture dependable. The evidence is strongest where it deserves to be strongest, and the speculation stays clearly labeled as speculation. Working this way requires more restraint than it may first appear. It would certainly make for a more dramatic story to announce that the nearest black hole has already been found, or that discovering it is only a matter of time. The evidence does not allow either conclusion. Instead, it points to a more complicated picture. A nearby black hole almost certainly exists. We can estimate how common such objects are, how they formed, and why they are difficult to detect. At the same time, there may never be a practical way to identify the closest one directly. Accepting all of those statements together is not a sign of uncertainty for its own sake. It is simply what the evidence supports. The unknown parts of the map are not fixed forever, though. Saying that the nearest isolated black hole may remain undiscovered does not mean future observations will stand still. New surveys will monitor enormous areas of the sky night after night, increasing the chances of catching the brief gravitational lensing events produced by isolated dark objects. Those observations should reveal more lone black holes than we have ever been able to detect before. The final releases from Gaia are also expected to uncover many additional dormant black holes through the subtle motions of the stars orbiting them. Every new detection will improve our picture of the local black hole population and reduce the gap between what we can demonstrate directly and what statistics already suggest. Even so, there is an important distinction to keep in mind. Most future discoveries will probably involve black holes that leave some observable signature, whether through a companion star or a measurable lensing event. Those detections may steadily reduce the distance to the nearest confirmed black hole, perhaps far below today's record. But if the closest object is an isolated wanderer that never produces an observable signal, it may remain beyond our reach. The confirmed record can continue moving inward while the true nearest black hole stays exactly where it has always been. The distance between those two ideas may become smaller over time. It may never disappear completely. That possibility is not a flaw in the search. It is one of the things the search itself has taught us. We have come a long way from a single number attached to a star in a distant constellation. We began with a distance of 1,560 light-years, treating it as the location of the nearest known black hole. Along the way, it became something else. It marked the limit of what we have confirmed, not necessarily the limit of what exists. We estimated an unseen population, distinguished evidence from inference, and followed the logic as far as it could honestly take us. All of that was done from a single planet, by observers who have never traveled beyond the solar system. And that is where the story finally turns back. Away from the scale of the Milky Way, and back to the room you are in right now. The same force that allowed us to infer the presence of a distant black hole is acting on you at this moment, close enough to feel without any telescope or detector. Throughout tonight, we have been following gravity across enormous distances. We used it to weigh objects we cannot see by measuring how they influence objects we can. That very same force is holding you against your bed. The steady pressure where your body meets the mattress comes from Earth's gravity acting on you every moment of your life. The equations that describe black holes are the same equations that describe this ordinary experience. The scale changes dramatically. The underlying physics does not. Think for a moment about what is happening beneath you. Every mountain, every ocean, and every layer inside the Earth contributes to the planet's gravitational pull. At the same time, your body pulls back on the Earth with exactly the same force. The difference is simply that Earth's enormous mass makes its response imperceptible. It is the same mutual attraction we saw between a star and its unseen companion. Gaia measured that tiny exchange by watching a star move around a shared center of mass. Right now, you and the Earth are part of the same physical relationship, governed by the same law. Gravity does not become a different force because one object is a black hole and the other is a person lying in bed. There is even a familiar number hidden inside that everyday experience. Near Earth's surface, gravity accelerates falling objects by about 9.8 meters per second every second. It is why a dropped cup falls, why climbing stairs takes effort, and why your body has weight at all. The same law, expressed through the same mathematics, also describes the motion of stars around invisible black holes thousands of light years away. The scales could hardly be more different. The physics is exactly the same. That continuity is one of the remarkable features of the universe. A single set of rules connects the familiar and the extraordinary. So where does that leave the black hole we have spent the night searching for? Somewhere in our galactic neighborhood, almost certainly closer than the nearest confirmed record, a collapsed star continues its quiet journey through the Milky Way. Even now, its gravity reaches you, unimaginably weak but perfectly real, just as the gravity of every star and galaxy reaches every other object in the universe. Of course, its pull is overwhelmed by the Earth beneath you, the walls around you, the moon, the sun, and countless nearer masses. It poses no danger. It asks nothing of us. It is simply another participant in the vast gravitational network that connects everything with mass. We have been studying that connection all night. It has been quietly including us the entire time. There is something reassuring in where this journey ends. We began by looking for a hidden black hole somewhere in the darkness beyond the stars. Along the way, we discovered that the same force guiding its motion is already part of the ordinary world around us. It is the force that keeps the moon in orbit, the Earth circling the sun, and your body resting where it is now. The black hole belongs to the same universe you do. It follows the same laws. The gravity that shapes its path is the gravity you have felt every day of your life. Understanding something so distant turns out to begin with something completely familiar. So, as the night grows quieter, there is nothing left to remember except that simple connection. You do not need to hold on to the distances, the masses, or the names of distant stars. The important part is much closer than that. Gravity has been quietly supporting you since the moment you were born. It is beneath every step you take, every object you lift, and every moment of rest. Tonight is no different. As your body settles into the mattress, you are experiencing the same universal force we have been following across the galaxy. The scale is different. The law is exactly the same. Thank you for spending this quiet part of the night with me. I hope this journey has left you with a little more curiosity about the universe, and perhaps a little more appreciation for the ordinary forces that quietly shape our everyday lives. Rest well. Gravity will keep doing what it has always done. Good night.